Good evening, everyone. Welcome to Week 11 interactive session of operating system fundamentals. So today, again, we'll go through the topics that was covered in the previous week, and then we will solve some of the sample questions which was given in previous year for assignment, as well as some other numerical problems as well, which basically we get kind of questions. Okay, we will start in a minute or two. Basically, in previous yes, majorly the topic covered in the previous lecture was basically on page fault and page replacement algorithms. So, page fault, then page replacement algorithms. So, we'll take a look at what page fault is and the various page replacement algorithms, and we'll try out some numericals. Okay, so when a particular program was trying to access the particular page that it needs at a given point of time, and if that particular page is not present in the memory, we call it as a page fault. So, for example, if a particular process it has 5 pages, P1, P2, P3, P4 and P5 in a demand paging situation. Currently, it is having only P1, P2, and P3 in the memory. Okay. Now, when it is trying to access some instruction that is present in P4 or present in P5, uh, when the CPU generates the address, it will do a lookup in the page table and it will observe that this page is not present in the main memory, and that is when we call it as a page fault. That is when a requested page is not in a memory. That is when we call it as a page fault. So when a page fault occurs, for the process to proceed further, we need to first bring the page from the secondary storage to the memory, and then the process need to start it. Okay. So so there are couple of steps that happens before this. So So when a requested page is not in memory, I said that a page fault occurs. Okay. So the normally how it works is there is this page table and we have main memory. This is page table itself is a main memory and we have main memory. And then we have the secondary storage. Secondary storage. So which is nothing but the frames. Now, when a particular process is requesting a particular page, if it is present in the page table, it directly goes to the main memory. Okay, so the amount of time it takes to read the data will be a page table access plus the main memory access. So we have already seen that to reduce this page table access memory time, we have something called as translation look-aside buffer, which is a faster memory, much faster than the regular memory. And so that will be there. And if TLB contains, then it's very TLB access time plus the main memory access time. If it is a TLB miss, then it will be a page table access plus the main memory access in case of a page, if the page is available in the memory. But if the page is not available in the memory, then there will be a page table access. The program will access the page, it will look up and it will not find the respective frame details, which implies that there is a page fault. Then this has we have to go to the secondary storage. Then we need to bring this particular page to the memory, and then we need to update the page table. So there are certain sets of tasks to be done when a page fault occurs. So the amount of time that one needs to spend on the page table on a page fault is also comparatively larger, and we in general call this time as page fault service time. So this page fault service time typically comprise of bringing back the page from the secondary storage. It of course comprise of accessing the page table, finding that is one memory access, finding that it is not there. Then it will go to the secondary memory. It will, before going to the secondary memory, we must identify a free frame. Where is a we need to find a free slot or free frame in the main memory. Then we will go to the secondary memory. We'll take the page and put it back into this identified main memory. And from the after that, the page table will be updated. Okay. So this whole process takes time, and this time is called as the page fault service time. So I hope you remember that when we discussed about TLB, we discussed the concept of TLB hit and TLB miss, and the effective memory access time when the TL in case of a TLB hit and a miss. So same thing applies for paging also. So if there is a hit, that is if it is available in the page table, then the memory access time will be much lesser. Whereas if it is a miss, that is when the content is not present in the main memory, we call it a page fault, and the amount of access time is higher. So we'll quickly recap that equation when it was for TLB, and similarly we have for page fault. Okay, so effective access time when we don't have any page fault. Let's consider we have a TLB also, and we don't have any page fault. In such scenario, effective access time without page fault for a will be a TLB equal to TELB hit ratio into TLB access time plus memory access time plus TLB miss rate into, we have seen L plus 1 into memory access time where L is the number of levels in the paging. So it's a single level paging, L will be 1. If it is double level paging, L will be 2. Like that. TLB access time. So this is when the page fault is not there, and effective access time with page fault is page fault rate into page fault service time plus this one, effective access time without page fault, plus 1 minus page fault rate into effective access time without page fault. So these are the basic formulas for how we compute the effective access time. Okay. Yeah. So in the lecture as there is an example that is discussed. Let's take a quick look at it. So assume that the memory access time is given as 200 nanoseconds and average page fault service time 8 millisecond. 8 into 10 power 6 nanoseconds. So when we are doing the computation, it has to be make sure that all the units are it's all in the same unit. All the time values are in the same unit. So effective access time will be here the page fault rate is not given, right? So it's 1 minus page fault rate into 200 nanosecond plus P into page fault service time, which is 200 minus 200p plus, which is 200 plus p into 799,800. Okay, so now if the SUPI is the page fault rate, now if we assume that it is 1 to the power of every 1000 access, which is 10 power minus 3, then effective access time will be 200 plus 10 to the power minus 3 into 799,800. Which is 200 plus 7,999 point 8, which is 8 8 1 99.8, which is this is in nanosecond, so we can tell that 8.2. This is in nanosecond, which is nothing but 8199.8 into 10 power minus 3 microsecond, which is 8.2 microsecond. So if we take the page fault rate as even lower, then the EAT will come down further. So instead of 10 power minus 3, if we make, for example, now if P equal to 1 power 1 by 10 power minus 6, then EAT, effective memory access time, will be 200 plus 7,999,800 into 10 power minus 6, which is 3 plus 3, which is 200 plus 7.99, which is 208. Okay, so this becomes the value 208. It will be nanosecond only. So as the page fault rate decreases, we can see that the effective access time have also dropped in. It's only 208 nanosecond because here page fault rate is very low. Whereas when a page fault rate is like 1,000 times more, the effective access time also have increased accordingly. So we need to have the page fault rate such a way that the effective access time is not very huge and the performance is not affected drastically. So let us see another example, another question on effective memory access time. Yeah. So the question was, we have a system with two-level paging, two-level paging scheme, and regular memory access time of 150 nanoseconds. Okay, the page fault service time is given as 8 millisecond. 8 millisecond. Okay, it is told that average instruction takes 100 nanosecond CPU time and 2 memory access time. It's given page fault service time is given as 8 millisecond. It is also given that there is a TLB and PLB hit ratio is 90%. Ratio is 90%, which is equal to 0.9, and page fault rate is 1 in 10K instructions, which is 1 by 10 power 4, 10 power minus 4. This is the page fault rate given. So the question is, what is the effective average instruction execution time? So this is the question. Okay. So what we have to find here is this memory access time. So average instruction takes 100 nanosecond CPU time plus 2 memory access time. So we need to find the how much time it take to access the memory. Okay, when there is a page fault with and without. Okay. So we know that without, when there is no page fault, the effective memory access time is the time it takes to access when we go via the TLB. Okay, so effective access time with page fault will be the memory access time plus the service time. Okay, so first we have to compute the memory access time without page fault. That is, when there is no page fault, it actually, since the TLB details are given, it is assumed that we have a TLB and the memory access is via TLB. So let's compute given that it's a two-level paging and the TLB hit ratio is 0.9, let's compute what is the effective access time using the initial formula. So, without page fault, the effective access time equal to TLB hit ratio, that is 0.9 into how much is the memory access time, that is 150 plus then TLB miss rate. In case if it is not there in the TLB, it is miss rate. Miss rate is 1 minus 0.9, which is 0.1. The hit rate is rate equal to 1 minus 0.9, which is 0.2. So this into L, we have seen that it is L plus 1 into memory access time, right? So here, since it's given that it is a two level, so if we go here, yeah, so this is the formula that we are using, TLB hit ratio into TLB access time plus memory access time. Since TLB access time is not mentioned in the question, we will assume it to be 0. Then, so TLB hit ratio is 0.9 into memory access time, which is given as 150 nanosecond. Then miss rate is 0.1. It is L plus 1 into memory access time. This again, we take this parameter TLB access time as 0. So here L is 2. So 2 plus 1, 3 into 150 nanosecond. 0.1 into 3 into 150. So it is 135 nanosecond plus 45 nanoseconds, which is 180 nanoseconds. So effective access time when there is no page fault is 180 nanoseconds. Okay. Now when there is a page fault, what is the formula? When there is a page fault, the formula is yeah. When there is a page fault, we have a page fault rate into page fault service time plus effective access time without page fault. So this is what we have just now computed, effective access time without page fault. And again, plus 1 minus page fault into this one. So now we substitute the computer formula in computed value in this particular formula. So we know that page fault is given as 10 power minus 4. Okay, so now access time with page fault equal to 10 page fault rate 10 power minus 4 into page fault service time is given as 8 millisecond. Okay, 8 millisecond plus effective access time. Effective access time, we have just computed it, 180 nanoseconds plus 1 minus 10 power minus 4 into effective access time, 180 nanoseconds. This is equal to 10 power minus 4 into 8 millisecond plus 10 power minus 4 into 180 nanosecond plus 180 nanosecond plus minus 10 power minus 4 into 180 nanoseconds. So this factor and this factor cancels out, which is nothing but 10 power minus 4 into 8 millisecond is nothing but 8 into 10 power 6 nanosecond. 8 into 10 power 6 nanosecond plus 180 nanosecond. So this will be 8 into 10 power 6 plus minus 4 plus 180 nanoseconds, which will be 8 into 100, 800 plus 180, which is 980 nanoseconds. So the effective access time without with page fault. So effective access time with page fault is 980 nanosecond. Now we have to find the average instruction execution time. Now it is given that average instruction execution time is equal to 100 nanosecond plus 2 into memory access time, effective access time, which is equal to 100 nanosecond plus 2 into effective memory access time is what we just found out, which is 980 nanoseconds, which is equal to 100 plus 1960 nanoseconds, which is nothing but 069 plus 110. So 20 nanoseconds is the average instruction execution time. So this is how generally problems will be asked in GATE and other examinations. So this was one such example wherein the effective memory access time is computed. Let's also take, so this was a little long one. Let's take few simple ones also. Started it in the reverse direction. Yeah, another question. So if the page fault service time is given as 10 milliseconds and average memory access time 20 nanoseconds. And page fault is given as 1 per 10 power 6 accesses. So page fault is given as 1 by 10 power 6, which is 10 power minus 6. So the question is, what is effective access time? Okay, here since there is no mention of TLB, and we will directly use the second question itself. So there we use the average memory access time as 20 nanoseconds. So it is the effective access time is page fault rate, which is 10 power minus 6 into page fault service time 10 millisecond, which is nothing but since some are in nanosecond and few are in millisecond, let's convert all into nanosecond. So 10 into 10 power 6. So millisecond is equal to 10 power 6 nanoseconds. Nanosecond plus the page fault service time. Sorry, page fault service time plus memory access time, which is 20 nanosecond plus 1 minus page fault 10 power minus 6 into memory access time. That is 20 nanoseconds. Okay. So which is equal to 10 power minus 6 into 10 into 10 power 6 nanosecond plus 20 into 10 power minus 6 plus 20 minus 20 into 10 power minus 6. So this and this will get cancelled out. Plus and minus. So this is again, this 2 will get cancelled out. This will be 10 plus 20 nanoseconds, which is equal to 30 nanoseconds. So the effective access time here is 30 nanoseconds. So this was one another example. Let's see one more example and then move on to page replacement algorithms. Another question is again given page fault service time. Then millisecond, which is nothing but 10 into okay, we'll see in which unit the other is given and then okay. So memory access time is given as my 1 microseconds. Okay. So 10 millisecond is 10 into 10 power 3 microseconds. And hit ratio, page fault or page, this is hit ratio, which is 1 minus page fault is what is given here, which is 1 minus page fault rate. That is given as 99.99%, which is 0.9999. Now, page fault rate is, PF rate is 0.0001. That is. So now effective access time, page fault rate. Page fault rate is 0.0001 into page fault service time, which is 10 into 10 power 3 microseconds, plus memory access time, which is 1 microseconds, plus page hit rate, that is 1 minus page fault, which is 0.9999 into 1 microseconds. Okay, that is, this is 10 power minus 4, right? This value is 10 power minus 4. 10 power sorry, 10 power minus 4 into 10 into 10 power 3 microsecond plus 0.0001 microsecond plus 0.9999 microsecond, which is this 2 adds up to 1. Here 10 power minus 4, and this is again 10 power 4, which is 10 power 0, which is again, so this is 10 power minus 4 plus 4, okay, which is 10 power 0 plus 1 microsecond, which is 1 plus 1, 2 microseconds, okay. So here are the effective access time is 2 microseconds. Okay, so now let's get back to the page replacement algorithms. So, yeah. So as we have seen that the page replacement will occur when there is a page fault. Okay. So when there is we have seen the page fault and how it increases the memory access time and all. So when a page fault occur, we need to bring in the page from the secondary storage to the main memory. So when we are trying to bring that, if there are no free frames available on the memory, then we have to remove one of the existing frame. We have to replace one of the existing frame. So if there are no free memory, no free frames, then we have to replace one of the existing frames. So this is nothing but page replacement. Okay. So we need to find a page in the memory such that even if we replace it, its impact on the overall system performance will be minimal. Okay, so there are certain algorithms that will help us decide which frame to be replaced. So it will help select the victim page. So page replacement algorithms helps to select the victim page. Select the victim page. Victim page is the page that will be replaced. Okay, so when a page is replaced, we get a place for to bring in the new Okay, so this might occur any number of times whenever there are no free frames in the memory. A particular victim frame will be chosen, and that would be replaced with a new frame from the secondary storage. Okay, then when we are replacing a particular page, so there is a already so this is the main memory, and we have chosen to replace this particular page. So when we are replacing this particular page, it is not possible that you just we can just bring in a new page and write over here. No, if this page was written, if the process which was using this page had written to this page, then we need to write back this page and then bring in a copy, new page. So to identify whether we need to write back this victim page or not is identified by using what is known as a modify bit or a dirty bit. So a dirty bit or a modify bit, dirty bit or modify bit. So a dirty bit or a modify bit is used to identify if there have been some modifications made to this page, and this tells the paging unit on the operating system that this particular page need to be written back to the secondary storage. So that's about dirty bit. So when we are when we are going for a page replacement, so there are certain steps that happen. So first we find a location uh, where we need load particular page. Okay, if you where we want to load that, so find a location on the memory. Okay, if there is no location found, if there is no free frames available, then we have to find a page for replacement. But if a free frame is available, then there is no need of page replacement. We can use the free frame. But if there is no free frame available, then we need to find a victim frame for a replacement. So first, the steps. What are the steps of page replacement? So first, we find a location of the desired page on the disk. Then find a free frame. If not, select a victim frame. Then if you are selecting a victim frame, check if dirty bit is set. Now after that, bring the desired page into the free frame or the chosen frame and update the frame tables accordingly. Update page tables accordingly. Fourth one is continue the process. Continue the process by restarting the execution, or normally the process, there will be a trap given and then the process execution will be restarted. Okay, so this is what majorly happens. So first we will identify the location on the disk for the page, then we will check if there is a free frame. Suppose there is a free frame, then just bring it over here. If suppose there was no free frame, this was a occupied frame, then and there are no free frames, all are occupied. Then choose this victim. Then check if it's 30-bit or not, and then write it out and then bring in the new page. So this is how page replacement, the steps in the page replacement. Okay. So in general, Each process will be given certain number of frames, and there is something called frame allocation algorithm. So frame allocation algorithm determines how many frames to be given to a particular process, and page replacement algorithms identify the victim frame such that the page fault rate, the intention is that the page fault rate would remain minimum. Okay, so that is the objective of the page replacement algorithm. The main objective is to choose a victim page, a page replacement algorithm, choose a victim frame. Minimum page that would further result in minimum page fault rate. Okay, so let us see a couple of algorithms. So one of the common algorithm is page replacement algorithm is FIFO, first in first out algorithm, as we have seen it in our this one CPU scheduling, first in, first out, same way. Here also FIFO algorithm is there. So here, as and when the pages comes to memory, they will be stored in a FIFO queue, first in, first out queue. And whenever there is a page fault, the page that came to memory earliest will be removed first. So let's see an example how this works. So let's take a page reference string 701 2. It's example from the lecture 701 201. And let's assume that there are three frames in memory at a time for a process. Okay, now let's see how this algorithm works. So first, as we have seen that we can have only three pages at a time. So this is how it will be. So initially it is all empty. So first 7 will come, then 0 will come, then 1 will come. Okay. Now when 2 has to come, we will replace 7 with 2 because 7 came first, right? So 2 will come here, 7 will be replaced. Okay, because it is a FIFA cube, right? So it's easy if you draw it like this. It's easy to grow it like this. So it starts with first 7, then 0, then 1. Okay, at any given point of time, only 3 will be there. So when 2 comes, 2 is not there in the memory. So 7 will be replaced and 2 will be placed. Okay, now 0 comes, 0 is already there. Okay, so there is no page fault required. But now the frame page number 3 comes, 3 is not there here. So we will replace the one that came first. So it will be in the starting of the queue. So 0 came, 0 is the earliest one who arrived in the queue. So 0 will be replaced with 4. Oh, sorry, not 4, 3. Yeah, 3. Okay. Now again 0 comes. 0 is not there. So now 1 will be replaced with 0. Okay. Now 4 will come. Again we will have a page fault. So we remove 2 and we keep 4. Now 2 will come. Again 2 is not there. So we remove 3 and 2. So this becomes easy to identify if we maintain it like this, no, first in first out. So the one who enters enter in this direction, enter in this direction, and it gets removed in this direction. Becomes easy to keep track of the frames or pages that came early. Okay. 2 came. Then after 2, again 3 is coming. So 3 is also not here. So 0 will be replaced and 3 will come in. So 3 is also a page fault. Now again 0 will come. 0 came. 0 is referenced, sorry. But 0 is not there. So again 4 is replaced by 0. Okay. Now 3 is referred. 3 is there in the memory. So there will not be a page fault. 0 is referred. 0 is there in the memory. There will not be a page fault. 3 is referred. 3 is there. There will not be a page fault. 2 is referred. 2 is also there. We won't have a page fault. Now, when 1 comes, 1 is not there. So 1, we need to go for a page replacement. So after 2, of this 3, 2 came to memory earlier. So 2 will be replaced and 1 will be brought in. Now again, when 2 is being referred, 3 will be replaced and 2 will be brought in. When 0 is referred, 0 is already there. So there is no page fault. 1 is referred, 1 is already there. Now when 7 is referred, 7 is not there. 0 is replaced and 7 is brought in. Now when 0 is referenced, 0 is not there. 1 will be replaced and 0 will be brought in. Now again when 1 is referred, 1 is not there. So 2 will be replaced, 1 will be brought in. Okay, so this is how so finally we have in the memory the pages 7, 0 and 1. So this is how the FIFO page replacement works. So whichever page came to the memory first, it will be replaced, irrespective of whether it was referred earlier or not. Okay, so to track the ages of the pages, Q can be used. Okay, but one interesting fact with FIFO is that it suffers from something called as Belladie's anomaly. That is, when we normally think, we assume that as the number of frames increase in the memory, the page fault rate will decrease. So, for example, here we are keeping 3 frames instead of 3. If we make it 5, what will be the situation? The assumption is that it will, ideally, that's what we think, right? When we have more frames, the page fault should be lesser. So let's see, as an example, if we make it 5, how this particular reference string is going to behave. Okay, so we have, instead of 3, let's have 5. So we will have 7, 0, 1, 2, then 0 is already there, and then I will have, then 3 is referred. So 7, 0, 1, 2, 3 is there in the memory. Then when 0 is referred, 0 is already there. 4 is referred, 4 is not there. So there will be a page replacement. 7 will be removed and 4 will be brought in. Okay, now 2 is there. So when page 2 is there, 3 is referred, 3 is there. 0 is referred, 0 is there. Again 3 is referred, 0 is there, 3 is there, 2 is there, 1 is there, 2 is there, 0 is there, 1 is there, 7 is not there. So 0 will be replaced with 7. Okay, now 0 is not there. So 1 will be replaced with 0, and the last reference is 1. 1 is not there, so 2 will be replaced with 1. So how many replacement we did here? initially it was all empty, so it is all a page fault only. Okay, but let's see the replacements alone here. So 1, 2, 1, 2, 3, 4. So we made four replacement, but we had totally 5 plus 4, 9 page fault, because initially when we started empty, we started all this 5 slots with no page in it. So when 7 was referred, 7 was not there, a page fault occurred, and then we brought in. But this was a scenario when a free frame was available. Okay, so replacement was not there, but a page fault occurred. For initial 0 also, it's the same. There was no replacement, but a page fault was there. So for all the 5, we had page fault initially, because initially none of the frames were in memory. 5 page faults we had. Then as the process progressed, referring to various pages, we had gone for 4 replacement with 4 page fault. So totally 5 plus 4, we have 9 page fault here. Whereas in the scenario, we can see that initially we had 3, right? So we had 3 page faults. Now let us see how many replacement we did. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. So we did 12 replacement plus the initial 3. So total page fault is 15, whereas in this scenario, it came down to 9. So this is what we expect normally. As we increase the number of frames, the page fault will decrease. But let's see another scenario, another reference string, like reference string. 1, 2, 3, 4, 1, 2, 5. 1, 2, 3, 4. 1, 2, 5. 1, 2, 3, 4, 5. Okay. So now let's see what will be the number of page faults if we have 3 and 4. Okay. Let's first take with 3 frames. So as I said, initially 1, 2, 3. So we have a free frame. So when the process referred to this particular page 1, there will be a page fault, but we have a free frame. So there will not be a page replacement here, but there is a page fault. So 1 will come, 2 will come, and 3 will come. So all these have a page fault. Okay. Now 4 is being referred. 4 is not there in the memory. So there will be a page fault followed by a page replacement. 1 will be replaced by 4. Now again 1 is referred. So 2 will be replaced and 1 will be brought in. So now after 2, now when 5 comes, 3 will be replaced and 5 will be brought in. Again 1 is referred, 1 is present. 2 is referred, 2 is not available, 4 will be replaced, 2 will be brought in. So it's a page fault plus replacement. Then when 3 is referred, 3 is not there in the memory, so it's a page fault plus a replacement. 4 is referred, again page fault plus replacement, and 5 is referred, again page fault plus replacement. So total number of page faults here is 1, 2, 3, 4, 5, 6, 7 plus the initial 3, which is 10. Now let's see what happens if we have 4 frames. We have 4 frames. We'll start with 1, 2, 3, 4. So we'll have that this will be a page fault. 2 is not there, page fault, but free frame is available, so there is no page replacement. 3 is not there, page fault, no replacement. 4 is not there, page fault, no replacement. Now 1 is there, 2 is there, 5 is not there, so a page fault and replacement. 1 is not there, page fault and replacement. 2 is not there, page fault and replacement. 3 is not there, page fault and replacement. 4 is not there. Sorry. Page fault and replacement. And 5 is not there, page fault and replacement. So now let's see how many replacements with page fault. 1, 1, 2, 3, 4, 5, 6. 6 plus 4. We have got 6 plus 4, 10 page faults. So this is known as um, Beladi's anomaly. That is, even if we give more frames, there is no improvement in the number of in the page fault rate. Okay, so this happens with FIFO policy, FIFO page replacement policy. Okay, now let's see one example, another example given the reference string of find the number of page faults for a FIFO. FIFO page replacement algorithm. Okay. So given the page reference string 3, 8, 2, 3, 9, 1, 6, 3, 8, 9, 3, 6, 2, 1, 3. 3, 9, 6, 3, 1, 3, 6, 2, 1, 3. So the question is, what is the number of page fault incurred before page replacement policy? Okay. So let's see. So first, it's given that there are 5 page frames. 5 page frames in memory. Okay. So initially 2, 3, 4, 5. So we bring in 3, 8, 2, 3, and 9, and all these are page faults because initially all these are empty. So page fault with no replacement. So now after that, when we refer one is not there. So 3 will be replaced and 1 is brought in. Then 6 is not there. 8 will be a page fault will occur. 8 is replaced and 6 is brought in. Now with 3, 3 is there. There is no page fault, no page replacement. 8, 8 is not there. Page fault and page replacement. 9 is referred. 9 is available in the memory. Again 3 is referred. 3 is available. There is no page fault. Now 6 is referred. 6 is also available. 2 is not available. So there is a page fault followed by a page replacement. for 2. Now 1 is available, 1 is there, 3 is not there. So 3 again a page fault followed by a replacement. So number of page faults here will be 1. This cross in the boxes shows the page fault with replacement, and the bottom crosses shows the initial page fault. So 1, 2, 1, 2, 3, 4, 5 plus 5. That is 10 page faults. Oh, okay. We made a mistake. 1 second. Let's do it again. So with the reference string, it is 3, 8, 2. 3 is already there. 9 and 1. So these are, so I made a mistake again writing 3 here. So 3, 8, 2, 3, 9, 1. So these are all initial page fault without replacement. Now when 6 comes, we'll have a replacement for 6. Then again 3 comes, we will have a replacement for 3. Then we'll have a replacement. No, there is no page fault for 9. There is no page fault for 3. There is no page fault for 6. There is no page fault for 2. There is no page fault for 1 and 3. So we brought in 3, 8, 2. 3 is already there. 9 and 1. So we have 5 frames in the memory. So 3, 8, 2, 9 and 1 in the memory. Okay. Now when 6 comes, 6 comes in. Now after that 3 comes in. So 3 is not there. 3 is brought in. Then 8. 8 is not there. 8 is brought into the memory. Then 9, it is present. 3 is present. 6 is present. 2 is not present. 2 is brought into the memory. Then 1 is present. And 3 is present. So totally, so initially I missed to check on 8 initially. So if we miss any of the reference string, the page fault will, the number of page faults that we arrive will go wrong. So when a long reference string is given, it's important that we don't miss any of them. So I missed 8 in the second trial. So yeah, so initially we had, sorry, we had 5 page faults followed by 4 other page fault plus replacement. So the total number of page fault here is initial 5 plus another 4, which is 9. Okay, so let's try one more. Hope we won't miss any. I won't miss any reference from this time. So page reference string is 4, 7, 6, 1, 7, 6, 1, 2, 7, 2. Now it's given that it's a three page frames. Okay, what is the total number of page fault? Then hit ratio and miss ratio. Okay, so let's write the in FIFO. So the number of three, it's given that we have initially three frames, so all of them will be empty. So we bring all of we first bring 4, 7, and 6. So all of this will be a page fault. But since we have three frames are free, there will not be replacement, but this is still be a page fault. Okay. Now when 1 comes, 4 will page fault will occur, 4 will be replaced and 1 will be brought in. Okay. Now when 7 comes, it is a hit. So there is no, because the page is already present, there is no page fault. 6 is also a hit. The 6 is already present. Now when 1 is referred, 1 is also a hit. 1 is also present. Now when 2 is referenced, 2 is not present in the memory. So it will be a page fault will followed by a replacement. So we'll bring in 2. We remove 7, bring in 2. Now again when 7 is referred, 7 is not there. So there will be a page fault followed by a replacement. 6 is replaced because it is first in first out, right? So in the queue now 6 is in the front. So it is DQ will be from here. So 6 was there in the front. So 6 will be removed and 7 will be brought in. Now, when 2 is referred, 2 is already present. So, we are done with the reference. So, now let's see how many page faults. So, initial 3 page faults followed by another 3 page faults and replacement. So, total number of page fault is equal to 6. And then hit ratio is equal to, miss ratio is equal to miss divided by total reference. So the miss is nothing but number of page faults, which is 6 divided by total number of reference was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, which is nothing but 0.6. So hit ratio will be 1 minus 0.6, which is 0.4. So this is about, sorry. About FIFO page replacement. Okay. So one more question. So these questions I'm taking from online, like old gate questions. So another question is, a system uses a FIFO policy for page replacement, and it have 4 page frames with pages loaded. So system first access 100 pages in some order. Okay. Access 100 pages in some order. And then access the same pages in reverse order. reverse order. Okay. So how many page faults will occur? So options are 196, 192, 197, and 195. Okay, so let us assume that the pages are 1 to 100 and they are accessed in the increasing order. So in the next attempt, it will be accessed in the decreasing order, and it's given that there are four page frames. So initially, 1, 2, 3, 4 will be brought in. Then 1 will be replaced by 5, 6, 7, 8, 9, 10, 11, 12, and this goes on until some pages will be replaced and 97, 98, 99, and 100 will come. Okay, so till this point, until 100 is reached, in this order, we have 100 page faults. Because there is no repetition of the same pages. It's accessed in this order. So every page got replaced. So 100 pages were accessed. So we had 100 page faults. Now, in the second part of the question, it's telling that first 100 pages are accessed in some order and the next access is in the reverse order. So after 100, it will be accessed in 100. First 1, 2, 3 up to 100 will be accessed, then followed by 100, 99, 98, 97, 96, 1. Okay. Now when this 100 is accessed, it is a hit. 99 is accessed, it is a hit. 98 is accessed, it's a hit. 97 is accessed, it's a hit. But from 96 onwards, again, we'll go for replacement. 96, 95, 94, 93. It will go on until 4, 3, 2, 1. So from here to here, we have another 96 page faults. So total page faults will be 100 plus 96, which will be 196. So that's the answer of this question. Okay. Now let's go to the other page replacement algorithm. The other algorithm that is discussed is there is something called an optimal algorithm. Optimal algorithm. Actually, it is a theoretical algorithm. Ideally, when we think of page replacement, we should be replacing the page that will not be used in the future, right? That is how we can minimize the number of page faults. So for that, we need the visibility into the future, which systems will not have. So this optimal page replacement algorithm uses is a theoretical algorithm which will replace the page which will not be used in the near future. So that is how the optimal page replacement algorithm uses, and this algorithm is mainly used for measuring how well a given algorithm performs. Okay, so it's normally not used. So we'll go to the next one. It's a theoretical one. Replaces the so go. So replace the page that will not be used for the longest period of time in the future. Replace the page go to LRU, that is least recently used. So in LRU, it will replace the page that will not be that was used long back in the past. So since we can keep track of the past, it's easier to implement this algorithm. So LRU replaced the page. So it replaced the page that has not been used for the longest period. So that is how LRU works. So let's take a look at one example, and we'll see how LRU works. So let's take the reference string from the lecture itself. So a long one, I'm going to mess it up. 7, 0, 1, 2, 0, 3, 0, 4, 2, 3, 0, 3, 2, 1, 2, 0, and 7, 0, 1, 0, 1, 7, 0, 1. 7, 0, 1, 2, 0, 3. Yeah. So, so here we need to keep track of the time when each page was accessed, and the one with the oldest time will be chosen for replacement. That is, it was not used in the recent past. So time will tell us which was the oldest one used, and that can be used for replacement. So if we assume that we have three pages, three page frames in memory. So initially we will have 7, then we have 0, and we have 1. Okay. So initial first 7 was accessed, 0 was accessed, and 1. 1 is comparatively the recent frame, 0 is the second recent, and 7 is the least recent here. So when 2 comes, 2 is not there, so it's a page fault. We need to go for a replacement. So we need to replace the one which was not used in the for the longest time in the past. So of the 3, 7 was not used for the longest time. So we replace 7. Okay, we replace 7 and we bring in 2. Okay, so now when 0 is coming, yeah, 0 is there, right? So 0 is already available, so we don't need to go and replace it. So what I normally do for LRU is I write it as a stack so that it's easy to understand which is the least recently used. So every time a new frame is used, it will be brought into the top of the stack. So if you assume this as the stack is growing in this direction. So this will be this is the top element at present. Okay. So now see, 0 is referred, right? So 0 becomes more recent than 1 and 2. So what we can do is it's a way that I do. It need not be followed. I just round up 0 because it's not a replacement, and I'll just bring 0 to the front. So to the front of the stack. Now this is where the top of the stack is, right? I want iPad. I need iPad. Oh my God. Yeah. So so now it's in the correct order. So 1 was the last used, second last used is 2, and 0 is the recently used. Now when we go for 3, when page 3 is referenced, so 3 is not there. There is a page fault and we need to replace. So now of this 3, 1 is the least recently used. So cross off 1 and bring in 3. to the top of the stack. So this is the front of the stack, the most recent one. So now again, 0 is accessed. So 0 is already available. So what we do is it's being accessed again. So just circle it and bring it to the front again. So it's just a technique that I use to ensure the stack and so that I can know which one to replace and which one to not. Okay. The box method sometimes confuses. So I go for this approach. So when you see this 0 is the most recent, 3 is the second last recent, and 2 is the oldest one. So now when 4 comes, we will be going for page replacement because 4 is not there and it's a page fault. So we bring in 4. Okay. Now again, now 2 comes, 2 is not there. We have 3, 0 and 4. 2 is not there. So it's a page fault. Replace 3 and bring in 2. Now again 3 comes. 3 is not there. So this is the least recently used. 0 is the least recently used frame. So replace that and bring in 3. Now when 0 comes, again it's a page fault. Of this 3, 4 is the least recently used one. So replace 4 and bring in 0. Now when 3 is referenced, 3 is already present. So just bring it to the front of the stack. There is no page fault or replacement. Now again 2 is referred, 2 is already present. Bring 2 to the front of the stack. So that 2 is the least recently used, 3 is the second recently used, and 0 is the last one. The next victim, 0 will be the next victim. So now when 1 is referred, yeah, so 0 will be taken, it will be replaced, and 1 will be brought in. Now again, when 2 is referred, yeah, 2 is already there, just bring it to the front of the stack. So that 2 is the least recently used now. When 0 is referred, we don't have 0, so we have to go for replacement. So bring in 0, remove 3. 1 is referred, yeah, we have 1 here, just bring 1 to the front of the stack. There is no page fault or replacement. Now when 7 is referred, yes, we don't have 7, so it's a page fault. We have to replace 2 and bring in 7. Now when 0 is used, just bring 0 to the front of the stack, and when 1 is referred, just bring it. So this is the LRU, least recently used algorithm. So we have to keep track of which is the oldest access and then replace that particular page. So this is one way I tried. It could be done in a using stack or any other approach as well. Okay. So this is the example of LRU page replacement. So maybe we can see a couple of more examples of LRU page replacement algorithms. So let's take the initial string itself, which we did for before. So page reference string. String is given as 383916389362 So we have 5-page frames. So initially 382 So the question, okay, let's get maybe I'll get the smaller one. 476176127 4761 761272. So system has 3-page frame. Question is what is the page fault, number, and hit and miss ratio for LRU. Okay. So we have 3, so 4, 7, and 6 will be having a page fault and will be brought into memory. So then sorry for that. Yeah, so 4, 7, 6 will be brought into memory with page fault without any replacement. Now the next page reference is 1, so which is not there, so there will be a page fault. So 4 will be replaced and 1 will be brought in. Now again, the next string referenced is 7, which is present. So we just move 7 to the front so that we can keep track of the least recently used. So now when 6 is referenced, yeah, 6 is also there. So just bring it to the front. Now when 1 is referred, yeah, 1 is also there. Bring it to the front to know that, yeah, now 1 is the least, 1 is the recently referred, 6 is the second recent, and 7 is the least recent one. So now when 2 is referred, we don't have 2, so we need to go for so it's a page fault and we need to go for a replacement. So the least recently used frame, which is 7, will be chosen for replacement. So now 2 will be brought in to the memory. Now again, when 7 is referred, it will be a page fault. So out of 2, 1, and 6, 6 is the least recently used one. So 6 will be chosen for a replacement, and then 7 will be brought in. And now again, when 2 is referenced, just bring 2 to the front. Okay, so the number of page fault is this crosses it will are the page faults actually. So initial 3 plus 1, 2, and 3. So these rounds are just rearrangement for understanding which one is the reason. So number of page faults is these crosses. So 1, 2, 3, 1, 2, 3, 4, 5, and 6. Now we have a total 1, 2, 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Total 10 references. Total 10 references, of which 6 is a miss. 6 misses or page fault we got. So miss ratio is 6 by 10, which is 0.6, and hit ratio is 1 minus 0.6, which is 0.4. Okay. So just quickly take one more example, then probably we'll come back to the problems after we discuss the previous year questions. We'll see one more exam to more and then it's all up on MCQ, so we can quickly wind it up here. So another reference string given us reference string 70120342230 32120170120342301. So here 4-page frames. So which means we can have 4 pages at a given point of time. So let's start. So initial 1, 2, 2. So 7, 0, 7, 0, 1 and 2. All 4 will be a miss. It's a page fault, but there is no replacement because it's a free frame. So we had 4 frames free. So though it's a page fault, there is no replacement. We bring in 7012. Now 0 is accessed, 0 is available. Just bring it in the front. It's a hit. 3 is not there, it's a miss. So the least recently used is 7. So we replace 7 and bring in 3. Now 4, it's again a miss. So the least recently used is 1 now. We replace 1 with 4. Now when 2 is referenced, yeah, 2 is already there. So we just bring it so that 2 will be the recently used one. So now again when 3 is referred, 3 is also there because it's the most recent. Just bring it front. Now 0 is referred, 0 is also there. Just bring it to the front. Now when 3 is referred, 3 is already there. Just bring it to the front. 2 is already there. Bring it to the front. 1 is referred. So 4 is the least recently used one. So 1 is not there. It's a page fault. So we need to replace 4 with 1. Now again 2 is referred. So just bring it to the front. 0 is referred. It's already present. It's a hit. Just bring it, make it most recent. 1 is referred. It's again a hit. Bring it more, make it more recent. So here the number of page faults is 1, 2, 3, 4, 5, 6, and 7. So we have got page fault equal to 7. Total references 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and 16. So 16 total references is 16, of which 7 is a miss. So miss ratio 7 by 16, which is 0.4375. Hit ratio is 9 by 16, which is 0.5625. Probably you can see that largest one also for Larry. So here again the page references is given as 3, 8, 2, 382, 391, 638, 638, 936, 36, 213, 382, 391, 638, 936, 213. So this is 5-page frame. So let's see the number of page fault. Okay, so 5 page frames. So this 5 will come to memory. 3 is referred. It will be a page fault. But a free frame will be there. So without replacement, 3 will be brought in. 8 is again a page fault. Without replacement, it is brought in. 2 without page fault, it's brought in. 3 already referred. Then 9 is brought in. And 1 is brought in. Okay. Now when 6 is referred, 6 is not there. So 6 is not there. So the least recently used among this is 8. So 8 will be, it's a page fault. 8 will be replaced with 6 will be brought in. Okay. Now when 3 is accessed, 3 is already there. We just bring it to the front. When 8 is accessed, 8 is not there. It's a page fault. It's a miss. So the least recently used one is 2. We replace this with 8. Now when 9 is accessed, 9 is already there. Just move it to the front to make it recent. Now 3 is already there. Bring it to the front to make it more recent. 6 is there. 6 is already there. It's a hit. So just bring 6 to the front to make it more recent. 2 is not there. 1, 8, 9, 3, 6. 2 is not there. So 1 is the least recently used one. We replace it and bring in 2. Now when 1 comes, again 1 is not there. So 8 is the least recently used. Replace it and bring 1 in. Now when 3 is accessed, move 3 to the front. So the number of page faults are 1, 2, 3, 4, 5. The initial 5 for applies 6, 7, 8, and 9. So page faults is totally 9. So here again, if you want to compute the miss ratio, it will be 9 by 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. 9 by 15. And hit ratio is will be 6 by 50. Okay. Yeah, so that's about page replacement, LRU page replacement. Okay. Now we'll move to there are other algorithms as well, like LRU approximation algorithm called second chance algorithm and all that. And enhanced second chance algorithm, counting algorithms, etc. are there. So we'll see. If not, we'll have another session coming up on, so that time I'll take up the problem. So let's first now finish the previous year question paper questions and then come back to this numerical. So previous year question paper. So the first question is again numerical. And then I'll share the other screen. Let me conclude this also. Here, yeah. So for the page reference string, 2, 230, 154, 230, 0, 1, 2, 5, 4, 3, 4, 2, 3, 5. 230, 154, 230, 154, 0, 1, 2, 5, 4, 3, 4, 1, 2, 3, 5. Compute the number of page fault following a LRU page replacement. Page fault for LRU with 3 memory frames initially empty. So let's do. So first 2, 3 and 0. All this will be page fault. It's given that initially the 3 frames are empty. Now when 1 is accessed, 2 will be replaced and 1 will be brought in. When 5 is accessed, 5 is not there, 3 will be replaced and 5 will be brought in. When 4 is referenced, 0 will be replaced and 4 will be brought in. Now when 0 is accessed, 1 is replaced and 0 is brought in. When 1 is accessed, 5 is replaced and 1 is brought in. When 2 is accessed, 4 is replaced and 2 is brought in. When 5 is accessed, again there is no 5, it's replaced and 5 is brought in. 4 again a page replacement, it's like before. 3. Now when 4 is accessed, we'll bring 4 to the front. Now when 2 is accessed, we'll bring 5. When 3 is accessed, we'll bring 3 to the front. When it's accessed, 4 will be replaced. After. So the total number of page fault is the initial 1, 2, 3, followed by all the other crosses. 3, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. So number of page faults is 40. Now, if we want to compute as an add-on the miss and hit ratio, it will be 14 by the total number of references 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 14 by 16 will be the miss ratio and hit ratio is very low, which is 2 by 16, which is the hit ratio. So this was one question. Now I'll share the screen. And so this was the question that was discussed, and here the answer is B. So the next question is an optimal page replacement algorithm always has the lowest page fault rate among all algorithms. Yeah, so as we discussed, optimal page replacement algorithm will have the lowest page fault rate, and it is actually used as a benchmark of measuring. Okay, it will never suffer from Belladie's anomaly. That is true. And it is difficult to implement as it needs future knowledge of the reference. That is also true. So the optimal page replacement algorithm, what it does is it will replace the page that will not be used in the near future. So we need to know the page access of a particular process, the future page access of a particular process, which is difficult. So that will be the best algorithm. So if we replace the page that will not be used in the near future, the number of page fault also will come down. So optimum page replacement algorithm, AS Pro, always the slowest page fault rate among all algorithm, will never suffer from Belladie's anomaly. That is true and is difficult. So here the answer is all of the above. Answer is D. Next question is select the incorrect statement regarding thrashing. So, thrashing is a scenario when a process just end up doing page fault, page replacement, page fault, That is, it will just swap in and swap out the pages. So it will swap in a new page. Immediately, it will need another page. It will again swap out this one, bring in a new one. Again, that will cause another page fault. And so it just end up doing this swap in and swap out. Instead of doing any progressing with the process execution. That is what thrashing is. So select the incorrect statement regarding thrashing. So local page replacement can limit thrashing, limit the effects of thrashing. The next is priority page replacement can limit the effects of thrashing. Yes. Then thrashing occurs when the size of all locality exceeds the memory size. Yes. And none of the above. So all these are actually true. These are priority page replacement and local page replacement actually limits the effects of thrashing. And thrashing occurs when the overall size of locality exceeds the memory size. So, for example, if we have 4 or 5 processes running and the total available memory frames is 10, whereas the locality of all these processes together is 15, then there will be thrashing. So the solution is to swap out or then otherwise go for local page replacement and bring in priority. So those are the solutions. So all these options are correct with respect to thrashing, and thus the answer is D. None of the above. Which of the following page replacement algorithm exhibits Baladi's anomaly? So Baladi's anomaly is actually exhibited by only FIFO, first in, first out. LRU and optimal page replacement algorithm does not exhibit the Baladi's anomaly. So Baladi's anomaly is that even after we increase the number of frames available for a process, its page fault rate increases. Okay, so that issue comes only with before first in, first out page replacement algorithm. So here the answer is B. Now, next question. When a page is selected for replacement and its modify bit is set. So, whenever, so modify bit is set to inform that there have some modification in this page and this page needs to be returned back to the secondary storage. Okay. So, if the modify bit is set, it doesn't mean that the page is clean. Okay. The page have been modified. Okay. It was read in from the disk. The page is dirty. Yes, another name is dirty. The page has been modified since it was read in from the disk and page is dirty. So uh, B and C together. So D gives the answer. So the answer here is D. Page has been modified since it was read in from the disk and the page is dirty. So select the correct order of basic page replacement. So I think we have seen we have discussed. So first we need to find out the location of the desired frame on the disk. Okay. Then after that, we need the page replacement algorithm will be used to choose if there is no free frame. Then once the page replacement algorithm chooses one victim frame, then the desired page is brought into the newly freed frame. So first is this one. Find the location of the desired frame found from the disk. Then page replacement algorithm is used in case there is no frame. After that, the desired page is brought in to newly freed frame and page and frame tables are updated, and after that the process is continued by restarting the instruction caused by the trap. Okay, so the option is 3, 1, 4, this one, so it is C. So, yeah. Now, the next is, okay, I'll keep the options here. Yeah. So the for the following reference, yeah. For the following reference, modify order pair which of the match the following columns. Okay. So reference bit 0, modify bit 0 means this is the best choice for replacing. So it implies that it is not recently referred and there is no write back near that. It's not modified also. So this will be the best page to replace. So one will match with this R. Okay. Match with R. Then reference bit 0 and modify bit 1. Reference bit 0 means it is not recently used, but modify bit 1 means this needs to be written out before replacement. So P. Okay, so sorry, P. So 2 will go to P. And 3 reference bit 1 and modify bit 0. So it implies that it is referenced recently, but it is not modified. So probably this page recently came and the probability that it would be used again soon is high. So 3 will be S and reference bit 1 and modify bit 1 is like so this again means that we need to write out before replacement and the probability that this will be used again is also high. So it goes to Q. So 1 will go to 1 to R. So these are the choices C and D, 1 to R. 2 will go to P. So 2 to P both have. 3 goes to S. 3 goes to S. 4 goes to Q. So the answer here is T. Okay. Now the next question. The aim of creating page replacement algorithm is to replace page faster, maximize page fault rate, minimize the page fault rate, and to allocate multiple pages to processes. The aim of creating page replacement algorithm. The aim of creating page replacement algorithm is to minimize the page fault rate. Okay. So the answer here is minimize the page fault rate. So the answer here is C. So this question, a page replacement occurs when free frames become available, a page fault occurs, and we need to bring the desired page into memory. Multiple pages are to be allocated to a process, none of the above. So when free frames become available, we don't need a page replacement. Page fault occur and we need to bring the desired page into memory, and this is partially correct. But if a page fault occur and we need to bring a desired page into memory, and if we have free frames available, then we don't need a page replacement. You need a page replacement only when page fault occur and there are no free frames available. But that is not mentioned here. So the next option is multiple pages are to be allocated. No. So none of these are correct. So the answer here is none of them. Q10. Which of the following statement is correct about replacement policy? Which of the following statement is correct about replacement policy? A local replacement policy considers all unblocked pages in main memory as candidates for replacement, regardless of which. So, local replacement, in case of local replacement, a page, the process will look at its pages and it will replace only its own frames pages. Okay, it will not replace any other process page. So the statement is incorrect. So here the question is, which of the following statement is correct? So global replacement policy shows more consistent per process performance. No, per process consistent performance is showed by local replacement policy. In local replacement policy, process selects a replacement from the set of all frames. No, it will, in local replacement policy, the process will select a replacement from its set of frames only, not from the set of all frames. Okay. And in case D is global replacement policy has greater throughput and S is more common. This is true. Global replacement policy actually, since the replacement and everything is global, it gives actually more throughput and is more, because of this higher throughput, it is more commonly used. So option D is the correct answer here. Yeah, so with this, we are done with this example questions from the previous year. I have couple of more problems. We can see that in the next class on working set and other things. Any doubts till now? If you have any doubts, you can post it in the chat. Were you able to follow the numericals that was discussed? Yeah, okay, then we'll wind up today's session. Thank you all for joining. In the next class, I will have I have one problem on working set on these few more problems on this FIFO and LARU, but yeah, we can see that in the next class. So, thank you all. Thank you. Bye.